Okay, so I wanted to do a video. I've gotten a little bump in subscribers, and I appreciate that. And I'm glad some people are interested in this. I think one of the more popular videos I do, or that I have, is when Saturn was Sun, and that video is basically illustrating how my take on how the solar system cycles. Um, Not necessarily as formed, but cycles. I don't know that we should go into how solar systems are formed, but rather the cycle that they're on. I think is far more telling for us and far more important information to study. Um, Now, what I want to do today is is discuss gravity, because gravity is actually my biggest beef with the contemporary science. Okay, um, I remember, when I was started uh, physics in college for mechanical engineering, and I thought, oh boy, this is finally I'm going to learn what gravity is. And I was so excited, and I can't remember which. It was within the first couple few lectures, and we did it. She had a lecture on projectile motion and stuff like that, right? And at the end of the lecture, I was like, well, what is causing the gravity? I thought, I raised my hand. What's causing the gravity? Finally, going to learn what's causing gravity, right? And I remember just this elderly Russian lady, real smart. She's very frank in her answers, and I was, I was puzzled. I said, so what causes gravity? She just looks at me. She goes, we don't know. I mean, I said, well, what do you? I mean, but what's producing the gravity? She goes, we don't know what produces gravity. All we know is how to measure it. And I was really disappointed because I thought that all my life, I had always thought about gravity and things like that, and I was always the type to ponder things, so I pondered gravity quite a bit, and I was really disappointed that I didn't get my answer for gravity. I don't know how much that actually relates to what we're going to talk about now, but I think it helps to be an inquisitive person in life. Um, I don't think we should just take information that's given to us um, as gospel. I think it has to go through a couple stages. The first stage is to really understand what they're telling you. And I think the second stage is to compare that understanding, um, and try to maybe apply or inject some other ideas into that understanding, whether those ideas complement it or run contrary to it. Either way, I think these are good exercises. I don't think anything um, is above being scrutinized. Um, Now, there are certain things that obviously have been that, gone through the rigors of being, empirically tested and confirmed, right? But there are other things that may not be as empirical as you're led to believe they are. And that's what I want to talk about, because my theory on planar forces is basically, I agree that there's gravity here on Earth, and we've tested that, and we know what that gravity is. Okay, We know how it acts as an acceleration on things on the Earth, close to the Earth, right? And we know that formula, right? And that is oh, that's the wrong A. I'm sorry. Which is mass times acceleration, right? So we know that gravity on Earth, this force of gravity that we feel, is equal to the mass times the acceleration, right? But my contention is this doesn't necessarily work everywhere in the universe, right? It's not a universal uh, equation that can be used universally. It can only be used, in my opinion, here directly, within, you know, uh, 25 miles of the Earth's surface, and outside of 25 miles of the Earth's surface. This goes away, right? Now, there is a planetary force that they use to describe the motion of the planets here in the solar system, and that's a different force, and that's a different equation, and that is F equals big G, right? And you got the mass of 1 and the mass of 2 divided by r squared, which is the distance, okay? Now, when we're talking about this, we're talking about this force is the force of gravity and humans here on Earth, okay? That's the force between these two items, okay? This gravity is the force, let's call it the sun and the Earth, right? Earth. I'm sorry, I'm having to write in a very awkward position for this, and and um, and that's the Earth, okay? So there's a force between these two, okay? And so I want to first talk, so everyone knows what this is, right? This is force. This force is actually your weight, okay? This is the force, this is the pounds of pressure that you put on the Earth, on the ground, okay? This is what that is. This acceleration is how fast you come to the Earth, okay? And it's based on your mass, okay? So that multiplied times your mass will give you the force, okay? So my problem here is I don't think that this equation is equal to that equation. And this equation has not really been empirically tested like we think it has been. And that's what this video is going to explain to you. Why I don't think that this equation can be used everywhere in the universe. Okay. So basically what we're saying is this force, what is this force right here? What are we saying this force really is? Okay. Basically, if you had a rope, okay, and you tied a ball at the end of this rope, okay, and you're swinging it, right, and you're swinging that rope, okay. Now you could feel that force of the ball at the end of this rope wants to fling away from you, right? But it can't fling away because it's being held by the string, which is being held by you, okay? So essentially you can think of that ball, okay, as the Earth, and you can think of yourself and the rope as the sun. And so the ball is swinging around you, but it can't go anywhere even though you know it wants to, just by doing this yourself at some point in your life. Everybody has swung something in the air, and you can feel that acceleration away from you. Okay, we're going to talk about what that is here in a moment. I'll do a quick explanation of what that is. Okay, but this force that we're talking about in this is that force that's pulling it back, that is pulling that, keeping that ball from flying away from you. All right. And there's actually, and I don't know how deep I want to go into this, but there are two components to that force. Okay. And one is the tangential force because it's tangent. Okay. And the other is the normal force. All right. And and these are vector forces. So the combination of those two actually give you the real force that is felt on that. Okay. The force that's actually felt on that is that. That's the F that we're talking about. That's the F that we're trying to figure out. Okay. Now, the problem with that I have with this is, what is mass? Okay. Well, mass is actually two components. Okay. Mass is the volume and what's called rho, which is the density, right? So the mass of something is two different things. It's a density and it's uh, a volume, right? So let's say, for instance, you see how small this is, right? This is just a little piece of plastic, right? It holds an SD card, okay? And it weighs, a couple grams, right? But imagine if this were made of lead, the whole thing, the exact excuse me, the exact same size, but it was made of lead. Okay, they would have two different masses, right? The mass of this would be far less than the mass of the one that were made of lead because the density is higher. Okay, it's heavier. We see it as heavier. It's not really heavier. It's only heavier because we live in a gravitational field, right? Um, but it's more, what it is it's more dense, okay, which increases that mass. So the reason I say that is because if we're saying this is the mass of the sun and this is the mass of the earth, we need to know what those densities are, right? And the problem with that is we don't have any empirical evidence of what the densities are of any planetary body whatsoever. Now, when you are being given explanations of the mechanics of our solar system, you're essentially, it's implied that we know what those densities are because you have to in order to know this force, right? And we know this force, right? Because we know if the earth is swinging around the sun at a certain speed and it's a certain distance, okay, so we have the distance and the speed of that going around here, we can get this force, right? But the only way we can know that force is if we know the mass of it, which means we have to know the density of it. The volume is easy. We can measure it. It's a sphere. We know what the volume of a sphere is. It's very simple to figure out, right? But the density we don't know, okay? Now, there are densities that have been assigned to the Earth, okay? And that's one of the things that I want to talk to you about is how they came up with that and why I think it's far more subjective than what they would lead you to believe. Now, There's also, see, this G is a constant, okay? And this A is a constant, okay? So this acceleration, you've heard of this acceleration to Earth. It's 9.81 meters per second squared, or 32.2 feet per second squared, whether you want to deal in British units or the metric units. But we're going to go ahead and use the metric units because it's getting even harder to just even find stuff in British units anymore. So, you know, even though I am an American and I'm far more um, acquainted with British units than I am with metric units, we're going to use metric. So this acceleration is 9.81 meters per second square. This G is 6.67 times 10 to the negative 11, okay? Which means it's a very small number. So they use this number for finding forces in the planetary motions, but this equation, but this equation is used for objects near Earth falling to Earth. Now, you can use this equation for this. In other words, I can put the mass of the Earth, my mass, my distance from the center of the Earth, along with that gravitational constant, and these F's will come out at the same number, right? And you should try it because it does work if you use the densities that they give you, right? If you use the density of Earth that's given to you. So this number, this G, has been tested, okay, and proven. Where's my quotes? Proven. And this acceleration has been approved. See, this A is actually a G as well. This is equal to the little g. The little g is the gravity that's associated with this, and the big G is the big gravitational pull of planetary bodies. Okay, I hope I'm doing a good job explaining this because this is really important stuff if you can follow along with what I'm saying. Now, this mass, or this acceleration, this is nailed down. We know what this is. Okay. We've tested things of all different sizes and densities, and we can cut these things apart and figure out the densities, and we can do all that stuff. And we know what this A is. We know that 9.81 meters per second square is a done deal. I would never argue with that. Of course, no one with half a brain cell left would argue with this 9.81 meters per second square. But this number, this G number, I'm going to tell you how they got that number, okay? And you might be surprised. And you can go in and figure this. This is all stuff on Wikipedia. Now this G number, this G number, which is how far down can you see? G equals 6.67 times 10 to minus 11. That means there's 11 decimal places in front of this number. Okay, so it's a really tiny number. This number, this constant, is what I want to talk about, how they got this constant, okay? And what relates to that specifically is the mass of the Earth, okay? If this is the mass of the sun, right? So let's talk about the mass of the Earth, how they got the mass of the Earth, and how they got this G number, okay? This G number is basically, it was very difficult. If you can imagine how hard it would be to figure out what this G number is, you're talking about two solid bodies, and their attraction to each other. It's very hard to detect unless you've got something with the mass of a planet, right? Because you're battling gravity inside Earth's next to Earth. Okay, so everything's falling to the Earth. So how are you going to measure two things that are coming together? You're not, because the gravity on Earth overshadows that to such a degree that it's very problematic to figure these out. But I'm going to tell you how they did it. Now, let's talk about the first thing they did to. First of all, all right. When Newton came up with this, okay, he surmised that at some point after coming up with all of this, he surmised that, well, must be the same gravity keeping planetary bodies in motion as well. Okay. So he said, okay, if this is the gravity on Earth, this gravity, Newton says, this gravity is the same throughout the universe. Okay. And in order to do that, obviously you can't use this equation. You have to switch over to this equation, which means you had to come up with a different G. Okay. Now Newton came up with a different G, if I remember correctly. It wasn't this number exactly. But it was fairly close. It was I think within 20%, because he basically said that the um, uh, density of the Earth must be 5 times water, 5 times the density of water, and that's how he came up with this uh, with this row for the Earth. Okay, for the density for the Earth. Now, a long time ago, back in the 1700s, someone did what they call a, a torsion experiment, okay, where they set up, uh, you have to look it up. Okay, it was the Cavendish experiment, okay, where he essentially had this huge rod, and he put these lead balls with a lot of mass on the end of them. You know, maybe it was a 40-foot rod, and he had it hanging from a rope. And he put another large mass object, and he basically measured. Let me get over here. He basically measured the twist in that. Okay, so he measured the twist in that rope. Okay, and that's why it's called torsion, because he was twisting the rope. It's a torsion experiment. Okay, where he was twisting that rope with the two masses. Okay, and so he came up with a number a lot closer than this. But this was done, and if you read about it, it was pretty crudely done. In today's uh, in today's technology, it would be considered extremely crudely done. And but remarkably, it's never been repeated, right? So they came up with this number back in like 1760, and they've never done anything to repeat the experiment since then. Okay? And if you have this number, you can get the Earth's uh, density, but you still have a problem with figuring out the sun's density. So you still really can't get the Earth's density from this number, because you have to either know the sun's density or the Earth's density along with this number to get one or the other. Okay. So what did they do? They came up with an experiment to get the Earth's density. And here's how they did it. In 1774, right, they basically found an isolated mountain. Okay, 1774, right, 250 years ago. They found an isolated mountain, okay, and they basically went just off of that mountain and dropped a plumb, right, down to the earth. A plumb is like a rope with something heavy uh, at the end of it, and that's what you use to get a perfectly vertical line because gravity's pulling on that perfectly, right? So basically, what they did is they took that plumb and they said, okay, this plumb, if there's no mountain, this plumb will point straight to the center of the earth. But if there's a mountain over there, that mass will push that plumb towards the mountain, which they figured out would be, you know, I think 2 minutes of a degree, 60 minutes to a degree. Okay, a very, very small amount. Okay, so I'm trying not to get too technical here, but I'm trying to give you the understanding of the crudeness that was used to measure this. And when I say crude, I only mean by today's standards. Believe me when I say what they did 250 years ago was absolutely remarkable. Truly, absolutely remarkable. These men were geniuses. These men were giants of their time. Okay, Newton, Cavendish, all of these guys who did all of these experiments that I'm looking at. Masklin, I guess this guy's name, who was in charge of this. Now, what they did back then was truly remarkable. But they came up with the Earth's density, okay, at 5.51 grams per centimeter cubed. Okay, so that's the row of the Earth. That's row of Earth. Okay, that's a sloppy, but so they came up with these numbers that we're using to predict the motions of bodies in our solar system. And my thing is you're basically given a mulligan on all this stuff. So because he came up with this number with this torsion experiment, and then they came up with this number with the uh, uh, um, density experiment to give the density of the Earth. And I could go into more detail about how he found that. It's actually really interesting. It's absolutely ingenious how they came up with this, to be honest with you. In both cases, both of these experiments were utterly genius. I mean, these men were so far ahead of their time. But nevertheless, it doesn't prove anything. Okay, it's one experiment with very, very subjective conditions, in my opinion. Okay, and so when you get this number and you get this number, now we have the density of the sun, right? Because I don't know how much math all of you have had, but you know, if once you're down to one unknown, you've got it. All you got to do is get down to one unknown, and you've got it. Um, and then basically, since you have the mass of the sun and the mass of the Earth based on these experiments that were done 250 years ago and not really verified since. Now we can do the densities of everything in the solar system. So we can say that Mars is this dense, Jupiter is this dense, Saturn's this dense, and but do we really know that, right? We're just plugging it in. We're just plugging in these densities. We didn't take core samples of Mars. We haven't even taken core samples of our Earth. And quite frankly, when they got this experiment, they only took so many samples of the mountain to get its density to come up with the density of the Earth, right? So when you really dig into this, it's really it's this stuff this is literally held together with duct tape. I'm telling you, okay. Um, do this information for yourself. Sit down and write it all. I've written all this stuff out, and then start looking at different densities of different planets that they come up with, and see if it even makes any sense. Right? Um, Also, do the different densities of metals and things like that. Just start looking at all the different densities and comparing them to the densities of the planetary bodies and things like that, right? So that's why it's my contention that this this works absolutely. This this was kind of force fed, okay? Because they wanted this to work everywhere, so they came up with this, right? But what if this is really, this is not empirical. I don't care what anybody says. This is empirical. This is not empirical. The density of our Earth has not been known to us through empirical evidence. We have only dug down in our Earth as deep as, I think there was a Russian crew that reached 10 miles. Our Earth is 4,000 miles from the surface to the center. We have dug 10 miles. Now, granted, we have, we have ultrasonic waves and stuff, and we can measure densities with those, and I don't know how far deep we can go with those. 25 miles? I'll give you 100. I'll give you 100 miles measuring the densities with with waves, okay, with sound waves or whatever other kind of wave you want to use, okay. But this is simply not empirically proven. And as long as you have that floating mass out there, that floating volume, as long as you have this, right, and you say you know the mass of the Earth, you've got a mulligan to figure everything out. Everything else can work. You can make it work because you just change the density of it to fit this. All you do is change the density of that. You change the density of Mars. You calculate the density of all the gas giants. You calculate the density of all the rock planets. The density of the Earth is reached from what we say the density of I'm sorry, the density of the sun is reached from what we say is the density of the Earth. Okay, you've got a complete and utter mulligan. It doesn't matter as long as you say, if you say this is in stone and that's in stone, but they're not in stone. They're nowhere near in stone. Okay, now they've got it all to look nice, but here's the problem. Okay, so let me tell you, this is why, and that's why, if you want to go back and watch, and I'm going to touch on it, but I go really deep into another video, which is called the non-existing black hole. Okay. And the reason I say that is the only reason that there are black holes or theorized black holes is because they got to get this theory to work on a galactic level now. It's not enough that it works on the Earth and it works in our solar system. Now we're saying it has to work on a galactic level. Well, how does that work on a galactic level? Because there are big problems on a galactic level, right? Because you've got these huge galaxies, right? That are like that are millions of light years across or whatever number they want to pull, right? And then you got this little tiny star out there that's, it's millions of light years. How is it attracted to the center of this of that galaxy? How is that even possible, right? well, there must be a black hole inside that middle of that galaxy with such mass that's incalculable that we just couldn't even imagine, and it just sucks everything in and destroys everything. And I'm making up all these stories about black holes. But the black holes are only there to make this theory work, or to make this formula work. That's it. If you didn't have this formula, you would not have black holes. And dark matter. Oh, there must be dark. Oh, there must be all kinds of dark matter holding this stuff together. Maybe, but is there proof of any of that stuff? Absolutely not. It is a house of cards. This whole side of this is a house of cards. There is nothing empirical about this right here. Nothing. But if you do some research and you go on Google and type, I mean, they know everything through that. Oh, I'm telling you, I've seen pictures of the moons of Saturn and Jupiter where they were sectioned off and they told you every layer of everything on those moons. They knew somehow. Okay, so the scientific community has really gotten a lot of mileage out of this. Um, but actually, most scientists, I think, would even agree that there's not a lot of evidence that this works. But it looks nice, and it's buttoned up really nicely. I mean, it's a three-piece suit. I mean, they got it looking good, right? But what's under it? You know, that's why I say I don't need any of this, okay? Because I think that this gravitational force on Earth is only on Earth. And our universe is formed, and all of the dynamics of the universe are a result of planar forces, right? So no, in other words, we have see, that's why I say, and if you watch all my other videos, they explain this really well. But basically, what I say is you have a physical plane, right? And when you have a physical plane, you have automatically forces on that physical plane. Okay. But what happens is this physical plane gets torn. And by the way, this physical plane, and I go into other videos, I, I basically deduce that the physical plane is the shell of a sphere. That's our universe. Our universe is the shell of a sphere. Okay, it's a physical plane. It is the thickness of an atom, and it is the shell of a sphere. Okay, when that shell rips, okay, that's when you see stars. That's when you see light. Otherwise, this shell is dark, kind of like how the Bible says. There was a darkness over the water. That's basically what the shell of the sphere would be. It was dark until it ripped, and then there was light. And when it rips, okay, it makes suns, and the bigger, it's in different dimensions. Okay, a huge rip in the shell is a galaxy. Okay, and inside that galaxy, the little rips are the suns, and probably solar systems, right? So basically what happens is when you rip this plane and it burns, you form a sun, because you're tearing you're actually tearing the physical plane. I think that's what a sun is. A star is the tearing of a physical plane, and I'm not going to go into that as deeper. My last couple videos go into that pretty good. So basically, if you look at this more, when you have a star like this tearing the physical plane, um, you still have those planar forces I was telling you about. Okay, right? And that's magnetism. That's what magnetism is. Okay, let me make sure this doesn't happen. That's magnetism. This planar force is magnetism. That's what it is. And the dynamics that are going on in here is a result of these planar forces and of the magnetism. And even the life that we see here on Earth, in my opinion, is the electricity that's formed from this magnetic field. If you know what electricity is a conductor breaking a magnetic flux. That's what we are. That's what you are. You're a conductor, and you're inside of a field, a magnetic field, a flux being broken, and that is life. That's the dynamics of our universe. It has nothing to do with the Big Bang. It has nothing to do with with gravity pulling it together and it's starting off with a big dust cloud. I mean, there's actually a lot of problems with this whole dust cloud, Big Bang dust cloud thing. I guess there were just different pockets of dust clouds everywhere. I don't know how they square up that hole exactly. I'm not sure they do. Um, they've even come up with some mathematics that show how this can all be held together, but then they have to say there's black magic. I mean, black holes and dark matter holding it all together. There's actually a better explanation for all of this, okay, for this part of it. And that is that we live on a physical plane and we're adding depth to that plane. And if you look into more of my videos, you'll see that reason we're adding depth to that plane. We're inside that plane. When we go inside, when our consciousness goes inside that plane and we occupy the physical plane, including these bodies, we're adding a perspective which increases the depth of the plane by adding that perspective in and of itself. That perspective also adds an element of time. It adds another dimension because there's inside a perspective, you have to have distance between your perspective and any object. And this is the time that surrounds the 3D, which is the 4D. And I don't know how much I want to get into all that with this, but basically what I wanted to do with this video is show you why I don't think that the gravitational constant here on Earth can be used and applied to the rest of our universe. I don't think it makes that much sense. I don't think it makes sense to do it. I don't think we need to do it. I think there's a better approach to all of this. I think there's a better understanding to all of this. Okay. And I think if you were to watch some of my other videos now, they will make a lot more sense as to why I don't believe that this gravity constant is the way it is, and is used in the universe, and it also and I also explain more in detail about the cycle of our solar system, and I think most solar systems are probably on similar cycles, and I think there's some different things that happen all over the universe, and I don't think that we know what we're seeing because in between these stars we don't know what it is. We don't know what that is. We don't know. Everyone says it's just empty space. I don't know that it's empty space. I don't know that it's anything. I don't know what that is, but it could also be having a big influence on what we interpret as what we see. Okay, so I hope that gets along. If you have any questions, I'd love to answer any question about this. But I think that I think we should know when something comes from the scientific community. I think we should be more informed as to how that information is gotten and how much proof it really is of of what we're saying. Because there's this theory leaves a lot of holes, a lot of holes, and it requires a lot of black magic to make it work. And I don't think we need to do that. I don't think that that's the approach we need to take. I think we need to take another look at our universe and another look at this physical plane and how it could be producing what we see in our night sky. Okay, so enjoy. Okay, so I had to make a quick note. The I made a mistake in this video, so I want to put a little take a couple minutes at the end of this video to add for an addendum to clarify something. Um, Prior to making this, I was always under the impression that um, the Cavendish experiment happened before any actual densities of the Earth were verified, um, and I was wrong. And I think the reason I was thinking that was because there had been guesstimates to what that uh, um, density was, and that's how they came up with their big G over here, right? So, but ultimately, what you have to remember is my overall, excuse me, my overall macro perspective of all of this is still correct, and I still stand by my claim that the that the rho for the Earth density and this big G, these two experiments, that these actual numbers that we use today are both based on experiments that happened before the year 1800. Okay, so not only that, but again, you have the density of the sun and the density of the Earth and this gravitational constant that's used for planetary bodies. As far as I'm concerned, they all float in a way that kind of gives you a mulligan. And you know that's the point that I was trying to stress throughout this video, was that the numbers that they're using to use this planetary uh, motion force is is I mean I just see a lot of I see a lot of I see a lot of openness to errors in it. Okay, and that's why I wanted to present this in this way so that people will take another look at my theory, which is the planar force theory, the normal force theory, that magnetism comes from being the base of and the cause of all the dynamics that's going on in our universe on a universal scale and galactic scale. Okay, so I just wanted to say that I didn't want to give a big explanation in words after explaining my mistake, but there is a mistake in there, so I did that. The chronology of that is that I had before was a little bit off. So, but the basic point that I was making holds true. Okay, so thanks again.